Hi everyone and welcome to the Learning Curve. This is the first in my special series that I am conducting on worked past paper questions for Calculus 1, particularly for business, social science, and economic students in universities studying at level 1. In this particular question, we will be using methods of integration. We are asked to evaluate the following integrals. You might find this formula useful. This formula is the formula for integration by parts. In the first integral, however, we'll be applying integration by substitution. We can recognize very quickly that we have a bracketed expression here that can be simplified to allow us to be able to arrive at the integral very easily. So for these kinds of problems, you generally want to use integration by substitution. So to use integration by substitution, I'm going to let u be equal to the term inside the bracket. So we're going to let u be equal to the term inside the bracket, which is 2x cubed minus 1. All right, so that's the first thing we want to do. We want to identify u. That's the first thing we want to do when we are carrying out integration by substitution. So we identify u here as the term inside the bracket. And the next thing to do is to find du dx, which means that we're going to differentiate this term u with respect to x. So let's go ahead and do that. We're going to find du dx, which means that we're going to differentiate 2x cubed minus 1 with respect to x. When we differentiate 2x cubed using the power rule, 3 comes down to the front of this expression and multiply by 2, giving us 6x, and we take 1 from the power of 3, giving us 2. And of course, the derivative of negative 1, which is a constant, is 0. So the derivative of 2x cubed minus 1 is 6x squared. Now we want to transpose this expression for du. So we need to express this in terms of du. And to express this in terms of du, in order to ensure that it is expressed with respect to x, we get du equals 6x squared dx. So du equals 6x squared dx. That is by making du the subject of the equation here, we multiply both sides of the equation by dx. So dx would cancel on the left hand side of the equation, and we would have dx multiplied by 6x squared on the right side. So by transposing for du here, du is equal to 6x squared dx. So again, when you're solving an integration by substitution problem, the first thing you want to do is to identify u. For problems of this nature, you want to set u equal to whatever term is inside the bracket. When we differentiate that, which is finding du dx, we get 6x squared as illustrated, and then we transpose for du so that du is expressed in terms of dx. That is necessary that we express du in terms of dx. We could go a little bit further with this and say du divided by 6. This is not an absolutely necessary step, but it might make things a little simpler later on. So we differentiate du both sides of the equation by 6 so that we're only left with x squared and dx on this side. All right, so that's an extra step that we could take at this stage, which will make simplification easier later on in the problem. Alright, so du upon 6 is equal to x squared dx, which is just a manipulation of this du equals 6x squared dx. So now that we have an expression for du, we need to now ensure that we rewrite the limits of integration. So we need to find the new limits of integration. And the new limits of integration will be found using the fact that u is equal to 2x cubed minus 1. So the initial limits of integration, or bounds of the integration that we're given here, are 1 and 0. So what I'm going to simply say here is that when x is equal to 1, and I know that these limits 1 and 0 are in terms of x because this integral is stated with respect to x, which is what dx means. But since we are re-expressing the integral with respect to u, or in terms of u, rather, we're re-expressing the integral in terms of u, then it means that we have to change the limits of integral, which are 1 and 0 in this case, and are with respect to x. We have to change them so that they are expressed with respect to u, since the entire problem will be carried out in terms of u. So when x is equal to 1, using the fact that u was assigned as 2x cubed minus 1, then we know that u is going to be equal to, substituting 1 for the function here, we would get 2 multiplied by, in the function, we would get 2 multiplied by 1 cube, take away 1. So this would give us a new upper limit of 2 minus 1, which is equal to 1. So what we're doing is that we're substituting the given upper limit and now the lower limit into the function that we assigned u as. Now we're going to say when x is equal to 0, which is the lower limit of the integral, when x is equal to 0, then u is equal to 2 multiplied by, here, it will insert 0 here for x, so it will be 2 multiplied by 0 cube minus 1. So 0 cube would be 0, so we'll get 0 minus 1, which is negative 1. So the new limits of my integral are 1 and negative 1. We had to find, as I indicated, new limits of the integration, because in order to integrate by substitution, which is the method we're using now, we need to re-express the entire integration problem in terms of u. So the new limits of the integral, which we're now going to proceed to carry out on this side. So what I'm going to say now, I'm going to restate this as the integral between 1 and 0 of 8x squared. So the integral between 1 and 0 of 8x squared bracket 2x cubed, which is the original problem as stated here. The integral of 8x squared into 2x cubed minus 1, all raised to the power of 7 with respect to x. This would now be re-expressed in terms of u as follows. It's going to be the integral between 1 and negative 1, because these are the new limits of the integration in terms of u as computed here. So this is the integral between 1 and negative 1 of 8, and this will be 8. Keep in mind that we would have expressed u as 2x cubed. We express u as 2x cubed minus 1. So this entire thing can be expressed as 8. This entire expression here can be re-expressed as 8 u to the 7th power, because 2x cubed minus 1 was expressed as the value of u, or the equivalent of u. So I replace the 2x cubed minus 1 with u. I will come back to addressing the x squared here. So this is 8u to the 7th power. And remember now that this now would be in terms of du. So I can write here du over dx. du over 6 rather. du over 6. Because du over 6 is the same as x squared dx. So that would take care of the x squared here, right? Because remember we found that du upon 6 is the same as x squared dx. So because du over 6 is the same as x squared dx, then x squared and dx here would be replaced by du over 6. Never mind the fact that they are not at the same place. You know the order of multiplication does not matter. So x squared dx would be replaced by du over 6, which we found it to be right here. So now we have set up the integral and rewritten it in terms of u. So from here, the integration process is going to be very simple. What we're going to do is that we're going to pull out the constant of 8 and 6. So this could be pulled out in front of the integration sign as 8 upon 6, or we could have simplified that to be 4 over 3. So this will be 8 upon 6, pulling out the constant, integral, and the integration limits here are -1 and 1. So again, we pull out the 8 upon 6, so that can be expressed as a fraction, 8 upon 6. We pull out the 8 upon 6, and that will be multiplied by the integral of u raised to the 7th power with respect to u, which is what the du means. Because remember, I indicated that we would have changed out from integrating with respect to x to integrating with respect to u. So that's what I now have. And so what we're going to do is to integrate u to the 7th. When you integrate a power term, you will add 1 to the power. So when I integrate here, this is going to become u to the power of 8. You add 1 to the power and divide by that power. This is the power rule of integration. The 8 over 6 remains at the front. So I put this in a little bracket, and then I write the limits of integration, which are 1 and -1 here. So the next step that we're going to carry out here is the substitution. So this is going to be equal to, we're going to substitute the upper limit of 1 and the lower limit of -1. So this will give me 8 upon 6 multiplied by, when I substitute the upper limit of 1 for u, I will get 1 raised to the 8th power. 1 raised to any positive power is going to give us 1. So 1 to the 8th power is going to give us 1. So we get 1/8. And we're going to minus the substitution of the lower limit into the simplified expression here, u to the 8 all upon 8. Now when I substitute -1 for u here, -1 raised to the 8th power is going to be 1, because we're raising -1 to an even power. Because we're raising -1 to an even power, the answer is going to be +1. So it's going to be +1 over 8, but because we're subtracting the integral, we're subtracting the substitution of the limits of the integral, then this is why this minus sign is here. When you're evaluating the simplified integral with the upper and lower bounds, you substitute the upper limit and minus the substitution of the lower limit. So this is why we end up with 1/8 minus 8 here. 1/8 minus 8 minus 1/8, rather 1/8 minus 1/8 is going to be 0, and when I multiply 0 by 8 over 6, the answer is going to be 0. So the answer for this integral is 0, and that takes care of the integration by substitution question number 1. Now let's look at this integration problem number 2. In number 2, we are going to use the integration by parts. So we're going to use integration by parts here, which means now that we're going to apply this formula, uv minus the integral of v du. Integration by parts is especially useful for integrating products, and it could have been applied in number 1 as well, but integration by substitution was more intuitive based on the factors that I mentioned earlier. So to integrate this by parts, we need to assign one of the terms as u. We're going to go ahead and assign the x here as u, and we're going to assign the e to the x as dv. So we need to assign one of the terms in the product as u and the other term in the product as dv. And then we're going to write down these terms. U is equal to x, and from u equal x, we need to find du. We need to differentiate u equal x with respect to x. So I'm going to find du dx, and du dx here is going to be equal to, when I differentiate x rather, we get 1, because the derivative of x, or 1x, is just the term in front of the x, which is 1. Just like if I had differentiated 5x, I would have gotten 5, but there's an invisible 1 in front of the x here. So when I differentiate this x, I will get 1. So this, of course, could simply be expressed as du equal dx. So this can be expressed as du equal dx, because we would multiply both sides of the equation by dx to get rid of dx on the left hand side, so that I'm only left with du, so that the expression is in terms of du. So du is equal to dx. And then for dv, now dv is equal to e to the 2x. And what we're going to do with e to the 2x here, from dv we need to derive v. So from u we need to derive du, which we did. And from dv we need to derive v, which we are going to do. So to derive v, we're going to actually integrate dv. So the integral of dv will give us v. So which means now that we're going to integrate e to the 2x. When you integrate an exponential function like this, all that happens is that you identify the coefficient of the variable in the power, which is 2. In other words, we differentiate the power. When we differentiate the power here, we would get 2, we would get 2, and we will divide the expression by that derivative of the power, which is 2. So the integral of e to the kx is simply e to the kx all divided by k. And we have applied that principle here to integrate e raised to the power of 2x. So we would have started the problem by assigning one term as u in the product and the other as dv. Then we went ahead to use those terms. We use u to derive du by differentiation, and we use dv to derive v by integration. Now that we have set up the problem this nicely, we are now ready to solve the integration problem. So we're going to say now that the integral of x e to the 2x, which is the original problem that we have here, the integral of x e to the 2x with respect to x, which is what the dx there means, is equal to, remember the formula is uv minus the integral of v du. This is the formula for integration by parts, typically used to integrate products. So what is u? U is what we assigned it as, which is x. So we assign u as x. And v was assigned as v was derived as e to the 2x upon 2. That's v. E to the 2x upon 2. That is the result that we found here from integrating dv. So that's e to the 2x over 2. Take away the integral of v, which again is e raised to the power of 2x upon 2 du. And we know that du is equal to dx. So I'm just going to place dx here because du is equal to dx. And we will carry out this integral with respect to x. So I can simply express this as x e to the 2x divided by 2, all divided by 2, by multiplying out the numerator here, x and e to the 2x, we get x e to the 2x all upon 2. Now we're going to integrate e to the 2x upon 2 here. You will remember that I said earlier the integral of e to the kx is e to the kx all upon k. The same principle applies here. Never mind the fact that we have a denominator of 2. that in fact could have been pulled out in front of the integral as a half integral of e to the 2x. So we can pull out constants in front of an integration sign. We're allowed to do that seamlessly. So now when we go about completing this integral, we would get the integral of e to the 2x upon 2 would become e to the 2x, and what we're going to do is that we're going to divide by the derivative of the power. The derivative of the power here, which is 2, we're going to divide by it, so I'm going to basically have 2 multiplied by 2 in the denominator, plus the constant of integration, which is c or k. So then this can be written finally as x e to the power of 2x upon 2, take away e raised to the power of 2x upon 2 multiplied by 2, which is 4, plus the constant of integration, which is k. And that would be the final answer. So we looked at integration by substitution, and we looked at an integration by parts problem. These are typical final examination problems in a Calculus 1 final exam pass paper at universities. I hope you found this lesson to be useful. Please look forward to much more. In my next lesson, I'll be doing an illustration of past paper solutions for Calculus 1 on double integration. Right, so you look out for that, problems in double integration, as I continue my series on the worked solutions to typical past paper questions in Calculus 1. I'm also currently doing installments for Introduction to Statistics, as well as mathematics for social sciences, business, and economics. Remember to like, share, and subscribe. Thank you, everyone.